Okay, hello everyone. Welcome to this special virtual edition of our usual general relativity problems class. So indeed, this is a GR problems class. And I will be experimenting with this new technology, so there may be some glitches. I'm going to ask everyone to bear with me. So what are we going to do today, remotely? We're going to study a problem with black holes. It's in the typical format of a problems class. I give you a problem and then I discuss the solution. So let me begin by giving you the problem. So the problem is the following. Remember, I like to discuss black hole physics with our pair, Romeo and Juliet. And typically Juliet is the one who falls into the black hole. So here we go. Suppose Juliet starts from rest at r equals to capital R in Schwarzschild, where capital R is larger than 2gm, so she is outside of the event horizon. If the event horizon is here, she starts out here at some r which is greater than 2gm, and then she just falls into the black hole. How much proper time does she feel before she hits the singularity? So really we're asking, what does Juliet experience when she falls into the black hole? And finally, the question says, work in Eddington-Finkelstein coordinates. Okay. All right, so how do we set up this problem? Well, the first thing we should do is remind ourselves what Eddington-Finkelstein coordinates are. So we look back in our notes, and if you recall, just because it's been a long time, let me remind you about some equations. The Schwarzschild metric in the normal Schwarzschild coordinates looks like this. It's 1 minus 2gm over r dt squared plus 1 minus 2gm over r inverse dr squared plus r squared d omega squared. So this is the Schwarzschild metric in the normal Schwarzschild coordinates. Okay? But now we're not going to work in Schwarzschild coordinates, because the problem is asking us to work in Eddington-Finkelstein coordinates. So we go and we look back at our notes and we remind ourselves what Eddington-Finkelstein coordinates were. Eddington-Finkelstein coordinates were very similar, except that the time coordinate t is not the same one. Instead, you use a time coordinate which I called v in lectures. And that time coordinate is regular at the black hole horizon. So if you look back at your notes, you can find this formula that I'm writing down right now. In Eddington-Finkelstein coordinates, the Schwarzschild metric looks like this. Okay, so this is Schwarzschild in Eddington-Finkelstein. Okay, so this thing V here is Eddington-Finkelstein time. Okay, so from now on, we're just going to drop the angular coordinates because nothing depends on them, so no more angular coordinates. And we're just going to work in V and in R. You should imagine that V is kind of like some kind of time coordinate, okay? And R is just the normal R. So let me just remind you, this metric is off-diagonal. We haven't worked too much with off-diagonal metrics. So let me just write down what this metric is explicitly in matrix notation. In lower index matrix notation, this metric looks like this. Okay, so these ones in the off-diagonal components are basically capturing this 2 that is here, the 2 dV/dr. Okay. So now basically we're trying to solve a problem about Juliet's experience as she falls into the black hole under free fall. And what that really means is we are trying to solve a geodesic equation. Okay. We're trying to understand Juliet's trajectory as she follows a geodesic into the black hole. Now, as you recall, there's always a two-step process in solving the geodesic equation. The first step is to always figure out what are the conserved quantities. Okay? What are the killing vectors in this problem? So if we stare at this metric, you can see that nothing depends on the Eddington-Finkelstein time v. Okay? nothing depends explicitly on v, that means v is a killing direction. So let me remind you what that means again. V is a killing direction. There's a killing vector with components only along v. So what that means is the following vector zeta, which is ddv, is a killing vector. Let me just write down for you the components of zeta explicitly. So the line that I just wrote down, that zeta is ddv, means that zeta's upper component is 1 and its its upper component in the v direction is 1 and its component in the r direction is 0. Okay? And now I can use the metric that I wrote down previously to lower the index. If I do that, what I find is that zeta mu turns out to be minus 1 minus 2 gm over r, 1. Okay? So these are the lower components of zeta mu. Now, what is the point of killing vectors? Again, the point of killing vectors is that if you dot them into the 4 velocity, you get a conserved quantity. What that means is that if x dot mu is Juliet's 4 velocity, then the following object, E, which is minus zeta mu, x dot mu, is constant along the geodesic. Okay, so let's now explicitly evaluate what that quantity E is in our case. So we have here E. If I just plug in, if I write out the components of x dot explicitly, and I take the dot product of that with zeta mu, what I find is that E turns out to be just 1 minus 2 gm over r, v dot minus r dot. Okay? So the point is, this quantity is constant along the geodesic. All right. Typically, at this point, I would pause and ask for questions, but that seems silly right now, so I'm just going to pause to give you a second to stare at this on your computer screen. Great. Okay, moving on. So here I have this quantity E, which is constant along the geodesic. Now, if I carry on, what I now want to do is go to the second step in the two-step program of solving the geodesic equation. Remember, the second step in this program is always to use the normalization of the 4 velocity. Okay. In other words, I want to use the fact that for a time-like trajectory, the following quantity is always equal to exactly minus 1. Okay. Now again, the components of x mu dot are v dot r dot. Okay, where again I'm ignoring the angular directions. And so if I use the metric that I wrote down previously, then what I find is that this equation right here results in 1 minus 2 gm over r v dot squared minus 2 v dot r dot equals to 1. Okay? All right, where obviously I multiplied through by an overall minus sign. So this is a constraint between v dot and r dot. And now the point is, I can now replace v dot with E. In other words, I can use the expression that we derived previously, this expression right here. Let me try to draw a line around it. This expression right here, I can now use that in this expression to get rid of v dot in terms of E. If I do that, what I find is minus r dot squared plus E squared equals to 1 minus 2gm over r. Okay, so this is great. This is a good equation. Let's take a second and stare at this. Have we seen this before? In fact, we have. You might remember we derived an extremely similar equation when we were solving the geodesic equation in the normal Schwarzschild coordinates, not using all this fancy Eddington-Finkelstein stuff. We derived, in fact, exactly the same equation. And the reason why is actually it turns out the killing vector partial t, where t is Schwarzschild time, is actually the same vector as partial zeta. Sorry. Okay. Oh, excuse me. That's not what I meant to say. It's the same vector as partial v. Okay. However, it is not true that dt is equal to dv. Okay. This earlier relation is true. So the partial derivative in that direction is the same, but the one form dt is not equal to the one form dv. And this is something that's not really important for this problem. It's just something to think about if you ever have a moment. Okay, in any case, let's forget about that. It's not really important. We have here this equation, minus r dot squared plus E squared equals to 1 minus 2gm over r. And now we can use that to figure out the solution to our problem. And how do we do that next? Well, first we are going to plug in the initial conditions in our problem. All right, so what are the initial conditions? Remember, when Juliet is at r equals to capital R, then she is at rest. And what that implies is that r dot equals to 0 when r equals to r. Okay. So what does that mean? Let's go back and stare at this equation here. What this means is that when little r equals to big R, r dot equals to 0, and therefore we can solve for capital E in terms of big R. We get just that E squared equals to 1 minus 2gm over big R. Okay? So this constant of the motion E, we have solved for that in terms of big R. Okay, so far so good. Plugging that in, we get the following equation. We have that r squared equals to 2gm 1 over little r minus 1 over big R. Okay, now how do we proceed? Well, remember, when I say r dot, what do I actually mean? I mean, r dot is, of course, exactly dr ds, where s is exactly the proper time along the geodesic. That is the meaning of this so-called affine parametrization, which we've discussed many times in this course so far. So in other words, s is the proper time along the geodesic. If we know what dr by ds is, we can integrate that to find what s is as a function of r. So just to go through the steps very, very painfully, we have that dr by ds squared equals to 2gm 1 over little r minus 1 over big R. What that means is, if you want to figure out how much s changes along the trajectory, you can just solve for ds as a function of r from the above equation, and then you can just integrate like this. So I want to start out at big R, but I want to end up at 0, because r equals to 0 is the singularity. Okay? And the integrand is just 1 over little r minus 1 over big R minus a half. Okay, so this is it. right. So here we now have an integral expression, okay? What I did was I just solved for the change in S from the change in R from this expression above. I plugged that into here. Then I integrated from R equals to big R, where Juliet starts, all the way down to R equals to 0, where Juliet ends. And this expression here tells me how much proper time elapses along Juliet's geodesic, and that is delta S. Okay, so the interesting part of this is done. Now you have to actually do this integral. This involves a trig substitution. The point of this class is really not the trig substitutions and doing the integrals, so I'm not actually going to do the integral. Let's just stare at this and make sure that the integral is finite. The integral is finite because when little r approaches 0, everything is finite. It looks like 1 over r diverges, but of course this is raised to the power minus 1/2, so everything is completely fine. And if you do the integral, you get a finite answer. What you find is pi r to the 3/2 divided by 2 root 2 gm. Okay? So this is the answer to the integral, and I encourage you to figure out the trig substitution does this if you are interested in that. Okay? The main point here is just that it is finite. Okay, let's take a second and think about this. What is this quantity? This quantity is how much time Juliet measures before she hits the singularity, at which point, of course, she dies. So it's how much time she measures before her death at the singularity. And this expression makes a lot of sense, right? If you make if you make big R bigger, what that means is that Juliet was starting from further outside the black hole, so it makes sense that she lives for longer. If you make M bigger, the black hole is going to pull on her more strongly, so it makes sense that her time decreases. Okay? Okay. And finally, one thing to ponder. It turns out that this is how much time Juliet feels along the geodesic. Okay? But it turns out this is the maximum amount of time that she can feel. And the reason is the geodesic is an extremum of proper time. It is a maximum of proper time for a time like geodesic. And so if she tried to struggle around, for example, if she was actually on a rocket ship and she fired the rocket ship engines, that would only reduce this time. Okay? So this is really the maximum amount of time that she can feel once she crosses the black hole horizon. Okay, that is all for that problem. And now we're going to move on to the next problem. Okay, so now let's carry on to the next part of the problems class. And if you want, I encourage you, one of the remarkable features of this technology is that you can pause and go back to see this previous problem if you want to. Okay, anyway, so now let's carry on to the next problem. The next problem is the following. A rocket hovers at little r equals to big R, which is greater than 2 gm. Part A, what is its acceleration a mu equals to u mu grad mu u nu, where u nu is the floor velocity? This must be supplied by the rocket engines. That's part A. Part B, suddenly the engines fail, the crew decides to throw a part of the total mass of the spaceship into the black hole in an attempt to attain escape velocity for the rest. What is the fraction f that can make it out? Then there's a hint. Use the conservation of form momentum, which states that for a particle of mass m, the conserved quantity associated with the killing vector is actually the form momentum p mu equals to m u nu dotted into the killing vector zeta, that is m zeta nu u nu is conserved. If the mass is constant, this is the same as the conserved quantities discussed in lecture, but in this case the mass will change when the crew discards part of the spaceship. Okay, so let's come back to part B. Let's first think about part A. So what is part A asking us? So in part A, we have, again, a black hole, okay? And again, we have, this time, a rocket ship. I regret drawing it facing that way. Let me try again. We have a rocket ship, okay? And it is hovering at a fixed value of r, where r is greater than 2 gm, so it's outside the black hole event horizon. Now let's think about this. Because it's hovering and gravity's trying to pull it in, it must be doing something. It must be firing its rocket engines that will sort of exert a force that keeps it out. And the question is saying, what is the acceleration of the rocket ship? Okay, acceleration is provided by the rocket engines. And they give a definition of acceleration, which might not be entirely obvious in this general relativistic context. The acceleration is just u nu grad nu u nu. And it should seem reasonable to you this is the acceleration, because this is the quantity which is exactly zero along a geodesic. This is a very reasonable thing to be the acceleration. Okay, but our task now is to calculate this. We want to calculate a nu, which is defined to be this thing. Okay, so here we go. So let's begin. So the first thing we need to note is that, so what's happening in space and time? Let me just draw this sort of space-time picture. So I'm going to draw time going this way, space going this way. Now, the rocket ship is hovering, which means that it is not moving in R. Okay, so this is the world line of the rocket ship. It is not moving at all in R. However, it is moving in T. So remember, we always demand that the forward velocity be normalized to have norm -1. In this case, what that means is that the forward velocity has a component in the time direction. The component in the time direction is just 1 minus 2 gm over R. Remember, this is R equals to R here. And it's 0 in all of the other directions. Okay, so this is T, this is R, this is theta, and this is phi. And I realize I should probably remind you, or tell you rather, that in this problem, we're going back to the normal Schwarzschild metric. I'm just going to write it down yet one more time. We're just working with the normal Schwarzschild metric, okay? Not the Eddington-Finkelstein one. We're using the ordinary Schwarzschild time, okay? And I'm going to ignore the angular coordinates. So in these coordinates, we have a rocket ship which is moving only in time, and it's not moving in the R direction or theta and in phi. Okay, it's moving only in time. And the way in which I figured out what the value of its time, its movement in the time direction is by demanding that u squared equals to -1. Okay, our usual demand. Okay, that fixes the coefficient of the t dot term, this term right here. Okay, good. So that is the forward velocity. So now we have to calculate the acceleration. So let's do that. So what is the acceleration? The acceleration is u nu grad nu u nu. Okay. Now, what does this mean? Well, u nu only has a component which is non-zero in the time direction. So u nu is only non-zero in the time direction. So this index right here is therefore fixed to be time. So what I get is ut grad t u nu. Okay. Now we know what ut is from the previous slide. What is nabla t? Well, nabla t is partial t plus something involving the Christoffel symbol, all right? But this part, the partial t part, does not contribute because u nu is also constant, right? Remember, the rocket is hovering, it's not changing, so this doesn't actually contribute. The partial part in the covariant derivative does not contribute at all. It is only the Christoffel symbol part that contributes, okay? So let me just put some of these pieces together. I have then ut times nabla t. Now, what is nabla t? So what we get is t nu sigma u sigma. Okay? Where this is just coming from the usual structure of the covariant derivative. Okay? But now let's think about this sum. Again, the only component of u which is non-zero is the component in the time direction. So in fact, this is simpler than it looks. This is just ut gamma nu tt again ut. Okay. Okay. And let me just remind you that ut equals to 1 over the square root of 1 minus 2gm over r, where in our case, r is equal to big R. Okay, so this is as far as we can go without actually calculating something. Now, it turns out we really do actually need the Christoffel symbol. Okay. Now, it turns out that the only Christoffel symbol, so the only non-zero gamma tt nu is if nu equals to r. Okay. And it turns out to be gamma rtt equals to g is equal to gm over r cubed times r minus 2gm. Okay. And this is, for example, in the appendix of the lecture notes online, or you can calculate it or look it up anywhere, or write your favorite Mathematica program to calculate it for you. This you actually do need. Okay. Okay. And you can also calculate it by hand. It's only one coefficient, so you can just work it out. Now, okay, that's fine. So now we take this and we assemble all the pieces together. We use the fact that ut is equal to 1 over root 1 minus 2gm over r, and we use the fact that this gamma rtt equals to this. We plug both of these things into this formula right here, and what we find, after a tiny bit of algebra, is that a nu equals to 0 gm over r squared, 0 and 0. Okay? Where again, I'm using coordinates t, r, theta, and phi. Okay, let's stare at this formula for a second. At this point, we are almost done. We are actually, in fact, done, because the question is asking us for the acceleration vector, and we have calculated the acceleration vector. Okay, so we're done. Let's think about the answer for a second. The acceleration vector is pointing only in the r direction. That makes sense, right? Because the rocket ship is trying to fall radially inwards, so it makes sense that the acceleration you have to supply is radially outwards. Okay, that makes complete sense. Now, let's think for a second, what might you expect to happen as you approach the black hole horizon? You might think that maybe the acceleration needed would go to infinity or something like that, or something. And notice that here it does not. It appears that as r goes to 2gm, the answer is finite, right? Nothing here is diverging. Does that make sense? Let's think about that. And now, if you want more time to think about it, again, I guess you can just pause this recording and think about it forever. So I'll let you do that. Okay, good, you're back. So why is it finite? Does that make sense? The point here is, notice that these are components of a vector, and components of a vector are coordinate dependent objects. Okay? They're not scalars, so they depend on the coordinates you use. So in particular, what that means is the fact that the radial direction is, has some value doesn't really mean anything. We should calculate a scalar to figure out, how big the acceleration really is. So for example, we can compute the magnitude of the acceleration vector a squared. And indeed, if you use the metric to calculate that, there is a divergence coming from the fact that g lower rr has this factor in it. And what you find is that the acceleration vector, the magnitude of the acceleration, a squared, does indeed go to infinity as r goes to 2gm. Okay. So indeed, the rocket ship engine has to fire arbitrarily hard to keep the spaceship hovering there as you approach the horizon, and that should make sense. Okay, on to the final part of the problem. Let us go back and remember what the problem was. So what's happening now is that suddenly the engines fail. Okay, So the engines have failed, and the crew decides to throw a part of the total mass of the spaceship into the black hole. Now, so what's really happening here? We have here this black hole, and the crew has decided to do this dramatic thing. The engine's not working anymore, so they decide to throw in part of the mass and see how much of the rest of the mass can come out. Okay, they're destroying part of their black hole in an attempt to save the rest of the ship. Okay, what is the fraction f that can make it out? And now here are these words again about the conservation of form momentum. So the point here is that if you have a particle of mass m, the conserved quantity is actually the form momentum, which is m times the force velocity, dotted into the killing vector zeta. Now, if it's m times zeta nu u nu, which is conserved, it is not zeta nu u nu itself. Now, this is of course the same if the mass is constant, which is almost always the case, but it's not exactly the same thing here. So let's think about that very carefully. All right, so here we go. So let us now remind ourselves of the situation. So the engines have failed, okay? And what is happening is that the ship is breaking into two parts. All right. So let us call the two parts of the ship M1 and M2. All right. And the point is that the ship, we want to throw the part with M1 in, and the part associated with M2 will come out. Okay. Now, because the ship's engines have failed, everything is following a geodesic, so we can use all this conserved quantity stuff. Okay. Now, first of all, let's think for a second about what the initial energy is. Where by energy, I mean the conserved quantity associated with the killing vector that points in the time direction. So for example, if I have a ship of mass m, then the conserved quantity E is actually minus m zeta nu u nu. Okay? Where here zeta is the killing vector that points in the time direction. Okay? So a bit more explicitly, if I write u nu out as t dot r dot theta dot phi dot, then the energy of this ship E equals to plus m 1 minus 2 gm over r times t dot. Okay. Okay. So now let's again go back to this picture that I had where I have m1 going in and m2 coming out. Let's first ask about the initial energy. Okay. So the initial energy is the energy of the ship as a whole. In that case, m equals to m1 plus m2. Okay, we're dealing with the total m here. And therefore, the initial energy is equal to m1 plus m2 times 1 minus 2 gm over r times t dot. But remember, I worked out what t dot was. The ship is stationary at rest, which means t dot is equal to 1 over the square root of 1 minus 2 gm over capital R. And again, in fact, this R also is capital R because everything is starting out at this point. And let me put a subscript I on the EI because it's the initial energy. Okay, so this thing here is t dot at early times, at the initial time. So now if I put all of this together, what I find is that the initial energy EI equals to exactly m1 plus m2 times the square root of 1 minus 2 gm over r. Okay. Okay, So that's the initial energy. Now, what is the final energy? So, what's happened? Well, let's just try to be as optimistic as possible, okay? So the ship breaks into two pieces, this M1 that goes in and a piece M2 that goes out, okay? It turns out that by falling into the black hole, the energy associated with M1 can be made arbitrarily low. Let's not even worry about that. Let's just assume that there's no real contribution coming from that. That's really being as optimistic as possible. Let's focus only on the part coming from M2. So if we are as optimistic as possible, then the rest of the ship is precisely at rest when r goes to infinity. Okay? This is the most optimistic scenario. We have conserved energy as much as possible so that we're just barely making it out to infinity. Okay? So in other words, r dot equals to 0 when r goes to infinity. And of course, we're assuming theta dot and phi dot were always 0 all along. Okay? And finally, at infinity, if the ship is at rest, t dot equals to 1. Okay? Because r is infinity, and we have a formula for t dot as a function of r when the ship is at rest. So what all of that means is E final in the most optimistic scenario is just M2. Okay? So notice, by the way, that this formula here is really just saying that the ship at infinity is not moving. If I put back the factors of c squared, there would be a c squared here. In fact, let me do that in red. There is a c, wow, that did not work. Anyway, you get the idea. There is a c squared here, okay? And really this is just saying the final energy of the ship is just its rest mass. Okay, let me now delete the c squared again. So in any case, we have that EF equals to M2 and EI equals to this expression right here. And now the point is we need that EI equals to EF. Okay. Now that was the most optimistic scenario. Okay. If we equate those two things, then what we conclude is that EI equals to EF. That implies that M2 divided by M1 plus M2 equals to the square root of 1 minus 2 GM over capital R. That just came from equating those two. And this is the best that we can do. Okay? So what that actually means is this quantity here, of course, is exactly the fraction of the mass that makes it out. That fraction must be less than 1 minus 2 GM over R. That is what we have just shown. Okay. And this should again make sense. Notice, by the way, that as we approach the horizon, the fraction of the mass that survives becomes arbitrarily low, which is bad news for our astronauts. Okay. So that concludes this problems class. I will say that this whole thing is online in a more easily readable format. I encourage you to go take a look at the teched up version of this, which is in Duo. Okay. Thanks everyone. Goodbye.